we are following a scheme where every segment is numbered. Okay, and this is required because TCP has to remember that the transport layer service has to transport the segments in perfect order to the application layer. So segment numbering or segment has to be, there should be some sort of numbering to identify the order of segments. Now this initial segment number selection is very tricky business. This is what we were considering in the last class. Consider this, that the segment number, suppose the segment number start with 0 or something, then at certain point of time the connection crashed. Either the connection crashed or one of the members crashed. And then this parallelogram, blue colored parallelogram that is showed, that is based on a packet lifetime T. What is a packet lifetime T? A packet lifetime T is an estimate of the maximum time for which the packet can be in the network. Means either the packet within this lifetime T, either it will be delivered to the other party or it will be killed off by the on the way to the router, because some router it will exhaust its hop count. The hop count field, remember we discussed that maximum hop count can be set. If the hop count field is set to 0 because it is decreased at every router hop, the packet gets killed. Okay, it is no longer forwarded by that router. So these two out of these two will happen, and this will happen within time duration T. Now, suppose now at the second dotted line, I mean this after the crash, after certain point of time, the connection 2 is initialized, but this initialization is within a time period which is not outside the forbidden region based on the last sequence number. The last sequence number is a constant over time. Okay. So it was linearly increasing starting from 0. By the way, there is an approximation in this graph. Can anybody tell me whether this straight line is correct or not? What is the approximation involved here? I mean, intentionally it has been shown as a straight line. It should not actually be a straight line, but can anybody answer? Hello?
Sir, the sliding window protocols slide is up on the sharing. We're not able to view the graph.
Still sliding window protocol is there. Can you see now?
It's visible now.
Strange. Tell me earlier. Yeah, can you see now? So the
Yes,
concept is that there is a increasing sequence number over time. There is a packet lifetime T which defines a parallelogram called a forbidden zone. Why it's called forbidden zone? That is what we are trying to understand. The issue is that at some point of time, say the connection crashes, either the connection crashes because maybe one of the two agents crash. Now that agent crashes, one of the two communicating agents crash, and finally it comes up after certain duration of time, which is shown by this dotted line. The question is, what will be the initial segment number for the when it comes back? That is the question. So I have, before we go to that, I have another small question. That is, this is the initial sequence number. This is a plot of sequence number versus, sorry, this is a plot of sequence number versus time. Initial sequence number versus 0. This has been shown to be a straight line passing through the origin. Passing through the origin because it starts from 0, assuming. My question is, can you answer that this is an approximation? Actually, this straight line, it should not look like a straight line in practice. What it is actually, can you answer? What should it look like? So this is a straight line y equal to x, which takes on all real values of x and all real values of y. But sequence numbers are integers, okay, usually discrete integers. So this is actually a staircase kind of a thing, which has been shown to be, just for the sake of easy understanding, has been shown to be a straight line. Okay, so remember this. The real sequence numbers will be kind of a staircase kind of thing because it increases in steps, some discrete steps, and only takes on some discrete values. Anyways, now when connection 2 is initialized, this is within some packet lifetime t, which means that the packets which had been released in the previous connection potentially have still not reached the receiver. They are still in the network somewhere. Either they have not reached the receiver or they have not been killed off. Okay. Now, what should be the initial connection value for the new connection that has come up? So it cannot be something like this, because if it is something like this, okay, I mean, it suddenly starts at this level. There is a potential that the old packets with the same value and the new packet, that is all these new packets in the overlapped region of these two parallelograms, they will create confusion at the receiver. So how do you solve it? Well, one of the option is that you start at a connection 2 value, which is much higher than the connection 1 value. In the this forbidden zone parallelogram, it is much above it. Means the point at which connection 1 crashed, it had some value. Okay, and those packets with lesser values will remain alive in this parallelogram zone, in this time duration. Just initiate initial sequence value which is much above this, but this will create a discontinuity among the sequence number values. Remember that this one server had crashed and again it is coming up. Okay, so it is basically the same connection. So there will be a discontinuity in this segment numbers, which will create more difficulties in the protocol. Okay, but this probably will let you survive without any confusion. The second option is that you start at such a low value of initial segment numbers that now you are outside. I mean, again, you are outside the forbidden zone. This is a little difficult to understand. They are saying that we will reuse some old segment number values that has been used, which is fine, which is all done all the time, because segment number is finite. Ultimately, it will wrap around. If you are using some k number of bits, okay, after 2 power k segment numbers, it has to wrap around. Okay, so it will saying that I will now start at such a low value that it is guaranteed that within the value at which I've started, all the segment numbers at that value or below it have already gone out of the system. And as I increase my segment numbers, I will keep a difference with my forbidden zone. I will never overlap with the forbidden zone. But what is the complication with this solution? Well, remember, if these two denote a continuity of the same connection, then the last segment number really that was probably received is the segment number, last segment number, which was at the point at which the server crashed. Okay, and suddenly you are continuing that connection, but you are starting with a very low segment number. This will create more confusion at the receiver. So some way you have to resolve this, that well, I am using low starting segment numbers, but actually I'm continuing the same connection. So again, this is a complicated thing. Are you understanding, students? This is a slightly complicated, and this entire topic TCP, this and the next set of slides that we will cover, this entire chapter is probably the most complicated stuff of this entire course. Okay, so please pay attention. So this is about how to handle. What we studied was how to handle these are the two ways by which you can avoid. Now, what happens during a connection is being established and suppose a receiver receives two segments having the same sequence number. Okay. Okay, then what happens? So in that case, one of the ways, then the receiver then has to somehow identify that there is a delayed duplicate. Okay, that the packet has, this packet had actually been sent earlier. Okay, how do we identify? It has to identify from the sequence numbers that within a time duration t I have received this. But of course, it will need to know this time duration and all this stuff. Okay. One of the ways to solve this problem is that suppose the device crashes and you make it wait for a time duration t so that all its packets which had originated from it, okay, all of them either reach the destination or die down in the network, and then you start new connection. So even after waking up, you intentionally wait for this lifetime duration amount of time. But this is not a good solution because it affects the quality of service. Okay, your server is ready, but still defensively you have taken a defensive, quite conservative policy that you are making the server wait. Okay. Now, so the solution is you have to adjust the initial sequence numbers properly as we mentioned in the slides before. So how to do it? Okay. So there are two ways. Again, there are two possible ways of problem. One is in a new connection, the host sends too much data too fast so that it overlaps with the newly opened connection. Okay, what does it mean? It means that in this restart problem, it sends at a rate which has a slope, which straight line has a slope which is higher than the initial slope. Then it will go into the forbidden region. The second one is peculiar. The second one, the data rate is too slow. Okay. By the way, the maximum rate at which this will be a clock tick. Let me just correct. The maximum data rate at which this data can be sent is 1 segment per clock tick. Why? Because the segment numbers should not increase at beyond 1 segment per clock tick. The segment numbers are usually numbered in terms of clock ticks. Okay, clock is either it is a day of time clock, like your time second minute second based clock. And what is the minimum tick of a day of time clock? It is 1 second. But it can also be the system clock, which operates at a much higher frequency, but it also has discrete clock ticks. Okay, this is an important concept. Okay, so you decide your clock tick, but one condition you impose is that I will not send out more than 1 segment per clock tick. Per clock tick nowadays is a very, very short interval of time. For example, even if your clock speed is something like system clock speed is something like 1 gigahertz, that is a very large clock speed, right? It is your duration, clock tick duration is just 1 nanosecond. So you are saying that I have a constraint. I will not send out packets at a rate more than 1 per clock tick, 1 per nanosecond. Okay, so that is fine. That you can easily do. Okay, that when I wake up again, I will not suddenly break this constraint and start sending packets at a faster rate than what was my previous constraint. The second one is very peculiar. The second one is saying that, well, the data rate is too slow in the new connection. Okay. You have to remember one thing, that the sequence numbers actually wrap around. Okay, so what is happening here is that instead of one segment per clock tick, it is now releasing segments at a very slow rate, which is shown by this straight line with a smaller slope. Okay, earlier the slope was something like this, approximately one segment per clock tick. Okay, but now it is extremely slow rate it is going. And finally, this connection is a long connection which uses lot of segments, and finally this wrap around. Okay, finally the sequence numbers wrap around, because suppose you have dedicated 20 bits to the segment numbering scheme, which means after 2 power 20 segments, the segment numbers will start from 0 or something. So what happens is that segment number finally start from 0, 1, 2 again, and finally there is another new connection probably with whose segment number it kind of tries to interfere. Okay, so it is said that it enters the forbidden zone for the next connection from downwards. Here, if it increases, if it suddenly the slope increases, it will enter it, sorry, from the left hand side probably. Here it will enter it from the right hand side, the forbidden zone. Here it will enter the forbidden zone of the next connection from the left hand side. Okay, now how to solve it? Well, so the way to solve it is don't release segments so slow. Release segments slightly faster so that this slope of this straight line will increase. But even if the slope of these straight lines increase, as you can guess, it is inevitable, unavoidable that this straight line will meet the forbidden zone of the next connection at some point. At what point it will meet, that can be delayed by increasing the slope of this straight line. Okay, but it cannot be avoided if you are dedicating finite number of bits to denote sequence numbers, which is kind of kind of given that there is no way you can avoid. On a computer, there you cannot have infinite number of bits arithmetic. Okay, it will always be finite number of bit arithmetic. So this is a peculiar problem. So you have to stay below one segment per clock tick, and you also cannot be too slow in releasing segments. Now this is the problem. Too slow in releasing segments is not actually entirely in the transport entity's hand. Remember that the transport entity passes on segments, creates and passes on segments based on whatever has been given to it from the application layer. Now the rate at which the segments are released, that is controlled by the transport entity. We will study in detail all the algorithms that are applied to control this rate. Why are they applied? They are quite complicated. But to a certain extent, this also depends on the application layer, the rate at which the application layer is generating segments and passing it on to the transport entity. It is not entirely the transport entity's alone responsibility. Okay, so this creates a problem now that, well, too fast release of segments is a problem, and too slow release of segments is also a problem, and the too slow release of segments is not in my hand entirely. So something has to be, some scheme has to be come up with. Okay, so now that the scheme that is actually used in TCP is something which is was proposed by a person called Tomlinson in 1975. It was mentioned here how to select sequence numbers. First of all, he said that two main concepts. First of all, he said that always starting from sequence number 0 for a connection. Forget this concept. Okay, this is not acceptable. This will never work. Secondly, there should be some sort of randomness involved in this. Secondly, he said that both the sender and the receiver would actively help each other, okay, to keep the situation under control in case of any confusion happens. How will it do? Quite simple. If once the parties agree on this, first of all, there would not be the same sequence, initial sequence numbers need not be used by the sender and receiver. Initial sequence number need not start from 0 for either party. Thirdly, whenever a party contacts the other party, he should mention that I have just now received this sequence number message from you, and I mean it sends its own message with its own sequence number, but at the same time it says I just now received this sequence number. Your previous message that I received from you had this sequence number. Okay, just this much of extra information it sends back. This is called positive synchronization between sender and receiver. So each of them help each other in remembering or making sure that it is playing the game correctly. Okay, that it is not making any mistake. First of all, they agree. This is my sequence starting sequence number. This is my sequence starting. Say one party says my starting sequence number is, let me show you the example, then we will go back to the detail. This is called, so we will now see the connection establishment phase. Okay, this is called a three-way handshake.
It's still stuck on slide 23.
Hello?
Sir, it's still stuck on slide 23.
Can you see the which slide do you see now? How do we ensure this slide?
Yes, sir. 23.
Now, do you move to the next slide, adjusting the sending rate?
Yes, sir. It's visible.
And can you see three-way handshake now?
Yes, sir.
Okay. Can you see the slide if I keep it minimized, because it looks like slide transition is not working if I put it to the full screen mode. Is it okay?
Yeah, now it's working.
Okay. So host 1 and host 2 performs a three-way handshake to set up a connection. Let us understand this because this is important. Firstly, suppose host 1 wants to, how does this positive synchronization happen between sender and receiver, or the two hosts? We should not say sender receiver because both parties can send messages. We have to understand. Okay, so let's understand this three-way message. Firstly, the host sends a special message called a connection request message shown by CR, and it proposes that I am going to use my starting sequence number is going to be X. This choice of X we will come back. That is in the previous slide. We will come back to it. How does it select X? That is Tomlinson scheme. Even this is Tomlinson scheme. Okay, this thing is also Tomlinson scheme. We will come back to it, but say it somehow it determines and proposes that I am requesting a connection with you with my starting sequence number to be X. When host 2 gets this message, it replies back saying, I accept, using a special type of message called an acknowledge message. Okay, ACK is for acknowledge. So this ACK, this term will be used many times in our entire course. So please get used to it. It sends an acknowledge message saying that I am okay with the connection. Let's start the connection. My starting sequence number is going to be Y. Again, how it selects Y is not clear yet. We will come to it. And I am acknowledging that I have received your sequence last packet that I received from you, or the one that instead what it sends back is, instead of last packet that I received from you, it could have sent that also, but instead how the most commonly implemented things, and TCP also how it works, it sends back a number which is the next packet, sequence number of the next packet that I expect from you. So remember that the connection request, this does not correspond to sequence number X. The first segment that it sends, that has the sequence number X. So through the connection request message, it was saying that ultimately when I start sending data to you, my first segment will have sequence number X. Okay. Fine. So this thing actually it says that fine. I will send. I acknowledge X, and sorry, I acknowledge X means this name is slightly confusing, that it looks like as if I'm acknowledging I have received. It actually means that I'm expecting sequence number X from you next. And then host 1 knows that, well, this guy has decided to use the starting sequence number Y. So that it notes down. And it is okay with me using sequence number X onward. So it then sends a data packet with sequence number X and acknowledgement Y. Why acknowledgement Y? Because it tells host 2 that next when you send me data packet, its sequence number should be Y. Now I have a question. What would be the sequence number and ACK field value, sequence value and ACK field values for the first data packet that host 2 will send?
Sir, SEQ equals to Y and ACK equal to.
Yes, tell me. Yeah, which ones? Host 2 will send first data packet that host 2 sent, which has not been shown here. What will it have in the sequence field and acknowledgement fields?
Y and X respectively.
Y and X plus 1.
Y and X plus 1. Y and X it has already sent. After that, the state of the connection has changed because it has already received the first data packet with sequence number X. So next, it sends out its first data packet with its own starting sequence number Y. So its sequence number field will have Y, but its ACK field will have X plus 1 because the data from host 1 has already arrived that had X. So next it is expecting the segment number X plus 1. In this way, it continues. Okay, and the second data packet that is sent from host 1 to host 2 will have sequence number X plus 1, and if it has successfully received the data packet with number Y from host 2, its acknowledgement field will be Y plus 1. Okay, fine. Next, the second.
Sir?
Yes.
Sir?
Yeah.
I didn't understand why this SEQ is Y and SEK is X. Why do we need two
Why
numbers?
means what? I have not told you why.
Like,
How did it get the value? Is your question, how did it get the value X and Y? So X
sir,
is
can you, no, no,
say
no,
1000 and Y is say 5000. I'm just giving random examples. Is your question why is it 1000 and why is it 5000, or what is exactly your question?
no, sir. Can you please just explain this step again?
Okay. So we have seen that sequence number, starting sequence number selection for a transport layer connection is tricky business, because first of all, it makes it possible that the receiver would get repeatedly old packets. These are called delayed duplicates. Delayed version of packets it has already received and might with the same sequence numbers, and it might get confused. How can it get segments with the old sequence numbers? We have seen many cases. Some cases is when some server crashes and resends values with old within the forbidden zone. Some situations is when it starts sending data at a very fast rate after waking up. Some situation is when it sends data at a very slow rate after waking up. Many different situations can arise. No solution to this problem is very satisfactory, because the rate at which data segments will be created and sent out, there is a certain amount of control, but there is no absolute control, because many factors are at play. The network layer is completely out of our control. This expected lifetime T is an expected value, but like any statistical metric, it can vary. So we do not have an absolute control over the value T. We cannot guarantee that packets will, well, most likely packets will die down in an interval T, all will be successfully delivered, but there is no theoretical guarantee. All these issues exist. So Tomlinson in 1975 came up with an initial sequence number selection scheme, which we will study, and he came up with several handshaking mechanism protocols to initiate closed down connections, which uses something called positive synchronization. In positive synchronization, the two hosts that are communicating, other than sending and receiving data packets between themselves, they piggyback or superimpose certain additional information to help the other party. So to kind of remind the other party what type of expected behavior is to be got from them. Okay. An example is the connection establishment through a protocol called three-way handshake. I'm trying to explain this protocol, so please pay attention. In this situation, again, vertically downwards is time axis. There are two computers, okay, host 1 and host 2. Host 1 wants to initiate a connection with host 2. For this, it sends a special type of segment called connection request segment to host 2. In this connection request segment, there are two, not the connection request segment, but later on we will find that segments allow two fields. Okay, it allows more than two fields, but there are two fields. One of them is called the sequence number and the other is called the acknowledgement number. These are numerical fields. Okay. In the sequence number field, in the connection request frame, the sequence number field has a meaning that I am requesting, first of all, a connection request is a special type of a segment. In this segment, it is mentioned to host 2 that host 1 wants to start a connection, and host 1 has decided, based on some scheme which we will study very soon, that it is going to start from sequence number X. This X is a random value within a certain range. Say X is 1000. It can be anything, 1000, 1360, 14,755, something. How it got that value, we have not come to it, we'll come to it. Is it clear up to this? Is it clear? The connection request part is clear?
Yes, sir. Yes,
Fine.
sir.
After some time, the host 2 receives this connection request segment. Why did I say after some time? Because notice that the arrow moved downwards. If it had taken 0 time to connect from host 1 to host 2, the arrow would have been a vertical line. Because time is going downwards, the arrow goes downwards, means time is proceeding. It reaches host 2. Suppose it is successfully delivered to host 2. When host 2 receives the connection request packet, it says, okay, this is a special connection request packet coming from host 1. How did it know coming from host 1? Because host 1's IP address will be mentioned in those segments. Okay, fine. And it notices that the initial sequence number that is being proposed by host 1 for this its own segments is X. If host 2 has no problem with this choice, means it is okay to start a connection with host 1, it says, okay, I will now start a connection. It opens a connection with host 1 and it sends an acknowledgement segment back to host 2. This acknowledgement segment has two fields. One is a sequence number field and the other is an acknowledgement number field. This sequence number field, by the way, now corresponds to host 2 sequence number, not host 1 sequence number anymore. This is crucial to understand, okay? Now host 2 says, well, if I start the connection, my proposed starting sequence number is Y. So my first data packet will have a starting sequence number Y. And I am acknowledging you the sequence number that you have proposed X by putting the value X in the acknowledgement field. This means that the first data segment that host 1 will send will have a sequence number X. If this acknowledgement packet reaches host 1 perfectly, host 1 understands that host 2 has agreed to the connection with starting sequence number X for itself, and host 2 sequence number starting sequence number X for itself, and host 2's starting sequence number will be Y. So it sends the first data segment to host 2. If it is okay with the choice of Y, it has to be okay with the choice of X because it itself has proposed it. But if it is okay with the choice of Y, it says fine. It now sends out its own data segment. This data segment has a sequence number X, which means that this segment number is X. This X is no longer 0. Earlier schemes that we were seeing, this segment number was starting from 0 for a new connection. That will no longer happen. And it acknowledgement field has a value Y, which tells host 2 that if you send me the next data segment, that data segment should have a number Y. The next expected data segment from you is Y. Just like in the acknowledgement message, host 2 had said that by having the acknowledgement field to be X, that the next expected value is X. Exactly like that. Okay. Then I ask that suppose now host 2 sends its own data. So this is a bidirectional connection. Just like a telephone connection. TCP connection is a bidirectional connection. In a telephone connection, both parties can talk. Right. So host 2 can also send some data back to host 1. My question was that in the data segment that host sends back to host 1, what should be its sequence field value and what should be its acknowledgement field value? Can you answer?
Like y plus 1 and x, because y and x are used already.
Why y plus 1?
Because y was
Suddenly,
there in
has
the
it
acknowledgement.
till now has host to send anything with y? Firstly, you tell me. Has host
Yes.
till now sent any data packet with y sequence number?
No,
Then
no
why
data packet.
should the sequence number be y plus 1? It should be y. But the acknowledgement
Because-
field will be x plus 1. When something
Okay.
happens in this direction from right to left now, it sends its own data packet. Okay. So it has to send its own data packet to this. There, its starting sequence number will be not y plus 1, it will be y. It has not yet sent y. Host 1 is telling it that the next expected segment from you should have y. And it will send y, and in its acknowledgement field, it will have x plus 1 because it has successfully received something with sequence number x. To tell host 1 to remind host 1, look, your next task is to send x plus 1. In this way, they positively help each other in remembering what sequence number they should follow. Now let's see the next example, which is slightly tricky. Suppose a connection request has been set up. Okay. Later on, host 2 receives another old delayed duplicate from somewhere in the network, which was languishing somewhere, some router in the network. Suddenly it comes out and reaches it with a sequence number x. As usual, host 2 acknowledges it. It acknowledges it, saying that, well, okay, this looks to be a new sequence number. So my proposed new sequence number is y. I am okay with the connection. I'm acknowledging that I have received the connection request. I am okay to start the connection, but my starting sequence number will be y, which is also okay. And I'm acknowledging that your starting sequence number, next packet that you send, first data packet that you will send, will have x. Now, when this acknowledgement reaches host 1, it says, "Arey, I do not have any connection pending in which I have not anything pending in which my next data packet should be x for host 2. Why is host 2 saying that I expect something whose sequence number should be x? That means he must have got confused by receiving some delayed old duplicate connection request segment from my side. That's why he is proposing that I will set up a new connection with sequence number x. In that case, host 1 sends a reject message back to host y, saying, special reject message saying, I had received a request from you where you had proposed that your next expected sequence, your starting sequence number is Y, but I am rejecting this connection. I will not start this connection. And when host 2 receives a reject message, it wraps up the connection saying that no, host 1 has not agreed to this connection. Host 1 need not tell host 2 in the reject message explicitly why it rejected the message. That also it need not tell. If it rejects the connection, connection is rejected. Unless both parties, unless both parties exist, connection cannot proceed. Okay, so no confusion happens and host 2 wraps up. So why did nothing bad happen here? Well, because in this three-way handshake, in this protocol, host 2 had cleverly sent an extra parameter back to host 1 saying that then the next expected segment from you will have sequence number X, which helped host 1 identify, because it does not have any live connection whose next sequence number has to be X. Immediately it identifies that something is wrong and it gives up on the connection. So in this way, host 2 saved itself and it kind of made it easier for host 1 to identify that no new connection has to be initialized. Okay. Now, even more complicated. Here, multiple old duplicates are coming. Connection request is an old duplicate and some data is going to host 2, which has an acknowledgement field. That data packet has also kind of an old duplicate, which means the acknowledgement numbers are not valid. Okay, let's see what happens here. First, an old duplicate connection request reaches host 2. Fine. And host 2 sends back saying that I am acknowledging this. My initial starting sequence number is Y and I'm acknowledging X. Okay. Means I am expecting your next data packet should be X. Now, just after some time, host 2 receives another data segment saying sequence number X, as if this is the first data segment from host 1, but it is acknowledgement number is Z. The next expected segment from host 2 has number Z, whereas host 2 had just now said that I am okay with the connection, but my next segment I will send will have a sequence number Y. So this host 2 does not accept this data packet, saying that something is wrong, because if this guy had sent me this data packet as the reply after successfully receiving this acknowledgement that I sent just few times sometime back, it should have an acknowledgement field Y, because it should have told me that my next expected data segment should have a value Y. Instead, it is saying some value Z. So this is an old duplicate. I will not accept it. So it rejects it. What about host 1? Host 1 basically it is the old situation. Okay. It suddenly gets something for which it has no record. It is saying acknowledgement X, and host 1 will say, what is X? I don't have any live connection in which my next data segment will be X, live connection for host 2, for which my next data segment should have a number X. This must be a reply from host 2 to some old duplicate that he might have received. So let me immediately say that I am rejecting this connection. I will not start it. And it rejects this connection. Are you understanding? So neither host 2 gets fooled in starting a new connection, and neither host and 2 gets fooled in accepting some old data packet. And it will not, did start half-heartedly start the new connection with this acknowledgement packet, but it will close down the connection after it gets the reject message saying that no, this thing is, I mean, the other party has rejected the connection. There should be some sort of randomness in the starting values to enable this type of things. Okay, so that kind of the similar number should not be there in the segments for repeated connections, multiple connections. This is the moral of the story, that don't repeat values. Okay. Is this clear to you? We'll continue with this in tomorrow's class. Okay, it's a quite complicated topic. It's already 12. So read this from Tannenbaum if possible. We'll continue. Thank you.
Thank you, sir. Thank you, sir.
Thank you, sir.